Let's look at a practical example. We have u second plus 1/8 u prime plus u equals 3 times cosine of omega t. So omega is not fixed, it's a value that we want to check at different, we assign different values to it and see how the system responds to different frequencies of the forcing term. And we assigned boundary conditions, u at 0 is equal to 2 and u prime at 0 is equal to 0. So the forcing frequency omega will stay as an omega all the time. We have the general solution of the homogeneous equation that I'll just give to you, you can compute it, is exponential of minus t divided 16 times the linear combination of cosine and sine of square root of 255 divided 16 times time. And the particular solution that is on the form we expect r cos omega t minus delta. I have a MATLAB code that computes and plots the solution depending on omega. From the previous formulas, we can compute r as a function of omega and delta, small delta, as a function of omega. I just dropped the formulas here, you can check them out. We can also compute capital A and capital B as a dependent on r omega and delta omega. If you want to write them explicitly as function of omega, that's going to be quite messy. So let's look at this live script in MATLAB. We are finding the solutions of the oscillating spring with a certain forcing. The first step of this code, the first block, is just defining things. I'm defining capital delta, I'm defining r, I'm defining cos of delta and sine of delta. All of these are explicitly functions of omega and might be functions of themselves. For example, r is 3 divided delta of omega. It's just an application of the formulas. Small delta is the r cosine of cos delta. Once we have all these blocks, we can compute a and b as a function of r and delta, r and small delta. Actually, b is going to be a function of a, but all in all, this is something we can do. And we can compute the homogeneous solution and the full solution. We check that the initial conditions are true for all the omegas that we have. So for example, I test u at time 0 with omega equal to 1 and with omega equals to 0.5. If it's not 2, then it's a problem. Notice that the initial conditions actually only involve capital A. So if those are correct, but your solution is not correct, it's probably capital B that is wrong. And then I plot. I plot the forcing in a dashed red. I plot the full solution in blue and the homogeneous solution in cyan. And running the code, this is what we retrieve. For omega equals 0.3, let me make this bigger. Doesn't work. For omega equal to 0.3, we have, as we were, okay, this is not working as smoothly as I expected it to. Okay. Here we have what is being plotted. And for every choice of omega, 0.3, 0.5, 1, 2, and 3, we have a new plot. So for omega equal to 0.3, you see the in cyan, the homogeneous solution that will roughly look always the same. The only thing that is changing is the coefficients. The forcing term, that is this red dashed line, and the solution that you see starts oscillating at the same speed as the forcing term, disregarding the speed of the frequency of the homogeneous solution. Then we increase omega and we see how the forcing term and the homogeneous solution have a peak at the same time, giving a full solution that also has a peak at the same time. Here it's particularly interesting for omega equal to 1 because the homogeneous solution and the particular solution cancel each other out at the beginning. So you see that the homogeneous solution has big swings, but the particular solution has peaks at the same points but opposite peaks. That means that the particular solution has cancelled out the homogeneous solution. And what you actually see is the blue thing, that is oscillations getting bigger over time until the homogeneous solution disappears and you only see the forcing term. Something similar happened for omega equal to 2, only the homogeneous solution only cancels a little bit the tip of your full solution. So you have this full solution that seems to have like 2 peaks until it stabilizes when the homogeneous solution tends to 0. And this is an even funnier situation, omega equal to 3, the cancelling happens at multiple points. So here you see the forcing term, that is the one driven by omega, that oscillates very fast.